in actual practical applications. So, please.
Thank you, Hussein. So first of all, my name is Tommaso Macri. I work at Quera Computing. My connection to the ITAMP is that I spent a few months back in 2021, really towards the end of the pandemic. And in relation to the topics of this presentation, actually one of the platforms to perform quantum computing is actually neutral atoms. And that's why ITAMP, the Institute for Theoretical Atomic and Molecular and Optical Physics, is actually very relevant to the things that I will try to explain today.
In addition to the fact that one of the co-founders of the Q-Arrow is a former ITAMP
yes.
postdoc.
Yes, and I think actually many people transition to the ITAMP for workshops, activities. And Quera is a quantum company, so a quantum computing company that is based headquartered here in Boston, in Austin actually. So it might happen that either in the next few months or in the next few years, you will have the opportunity to actually see our quantum computers with your own eyes if you just stop by our headquarters. Okay, so let's see if it works. If not, I can just stay here. So Christian already told you a little bit about how
It doesn't work.
I don't think.
No, this is not the one.
Oh, that's Christian? Okay.
Yeah.
Oh, great.
Yeah.
Excellent. Okay, great. So, what is quantum computing? We already heard about the basic ingredients of quantum computers. Differently from classical computers that use bits, so zeros and ones, with quantum bits or qubits, we can actually create superpositions between the two. One of the simplest ideas to basically understand what a qubit is to think about a vector that can rotate, whose tip can rotate across basically a sphere. So you can create arbitrary superpositions of the two basis states that we call 0 and 1. But then a superposition can be, in principle, an arbitrary superposition with an amplitude and a phase. And here we go back to the concepts that were explained during the first presentation. There are other interesting features that make quantum computers actually powerful. For example, the idea of entanglement that Christian was trying to explain in simple terms. There are other interesting features, such as the one of parallelism, that allows us to basically test, in principle, many different solutions all at once. And why is quantum computing actually different in practice? Well, the fact is that many people say that quantum computers are actually much faster than classical computers. But I would like to highlight or emphasize also the fact that it is really a different paradigm to make computation. So in principle, when you want to do computation, no, it's not working. Oh, it's working. It's working. It's a quantum, so it's random. It's doing random things. So let me go back manually. So in principle, when you want to perform a computation, the idea is that you want to start with some input data. Then you have a device that performs some processing of that information. And eventually you want to extract that information, so the results of the computation, and potentially post-process it. So for example, making a graph, a plot, something that you can eventually interpret to the purpose of understanding how to go from the input to the output. So in for classical computers, like our outputs, we have bits, so zeros and ones, which can in principle be represented by electromagnetic signals, for example. Then you have gates, which are operations that you do on top of these bits. And the result is usually deterministic. So again, it's like doing 1 plus 3, it gives always 4. In quantum computing, instead, you have qubits. Again, you have superpositions of these two different states, basis states. You have, again, operations. Now we call these operations quantum gates. And then the result can be either probabilistic or deterministic, depending on the way in which you process information, but also it depends also on the way in which you create the state. So basically input information to your quantum processor. Why are quantum computers interesting in terms of practical utility? or for real life? Well, there are in principle many difficult problems, first of all, that are not actually easy to solve with classical computing systems. A series, I'm just listing a few of them. For example, designing new types of drugs. Drug design is actually very computationally intensive. There are applications in artificial intelligence, so AI or machine learning applications. Application in logistics, for example, to compute the fastest route to go from point A to point B. Applications in finance or financial services, like portfolio optimization. Suppose that you want to bet on a number of different stocks, but you want to hedge essentially the risk on top of that type of investment. There are ways, or there are applications or algorithms that were proposed in the context of quantum computing to potentially speed up certain types of calculations. Then, the one that looks probably most interesting to many of us, at least from, I think, the perspective of the postdocs here at the ITAMP, is the one of related to physics, in particular to quantum physics, which is the idea of the so-called quantum simulation that was proposed by this gentleman here. Do you know who this person is?
Richard Feynman?
Yes, this person is Richard Feynman. In the 80s, Richard Feynman essentially proposed the idea of simulating a complex quantum mechanical phenomenon in terms of a different quantum mechanical system that you can tune or control in a much better way. So it turns out that for many different applications, quantum computers are really one of the best, actually one of the best ways to simulate nature. So the idea of quantum simulation is really to use quantum computers or quantum simulators to simulate, to emulate, or to mimic the behavior of certain natural phenomena. And if you're interested, we can dig as deeper as you like on this, because this is a topic that I really like a lot. There are a number of interesting or famous algorithms. One of them was mentioned by Christian in his previous presentation, which is Shor's algorithm that has a very important application in terms of essentially factoring large data. And this is in principle, when we will have sufficiently powerful and scalable quantum computers, can threaten RSA encryption. But there are other types of algorithms, such as the so-called Grover's algorithm, that can speed up certain types of processes, like, for example, the problem of searching in a database. And the speed up here is not as huge as in the case of the Shor's algorithm, but is still better than what you could achieve with a classical computing system. Now the question is, how far are we from building a real quantum computer? Well, we are not yet there in the sense of having such powerful machines that we can actually tackle simultaneously all these potential applications. But we are not yet. We are not really at the beginning of this journey. There are different platforms and different companies, and many companies that are actually developing technology to build and commercialize quantum computing systems. And each one of these, as you see, focuses on very different physical systems in principle. The first one is the superconducting circuits, and we heard from one of the previous presentations what is the physical principle behind superconductivity. There are companies such as like IBM, Google, and AWS that are really developing these devices. And this is one of the most popular images of a quantum computer. It's the image of a kind of chandelier, where the goal here is to basically make the system, so cables and the chip that sits actually at the bottom, colder and colder in order to reach a superconducting state, right? There are other systems like trapedions that are developed by companies such as IonQ and Quantinuum. There are some specificities associated to each one of these systems, like for example, in the case of superconducting qubits, they are fast but relatively hard to control. Just take a look at the number of cables that you see here. It's really a mess. And if you think that in order to get useful quantum computers, you will need to have systems with hundreds of thousands or millions of qubits, And if each one of the qubits is controlled by at least 2 or 3 cables, you can imagine that you will need a space that is probably bigger than this room just to control a single quantum computer with hundreds of thousands of qubits. But luckily there are other systems like trapped ions. You probably know what an ion is. You know what an ion is, right? The difference between atoms. So there are like, how did you define ions? I forgot your definition, which was...
My definition.
Yeah, you had a very popular definition of an ion. It's a fake atom or what?
Oh yes, yes. And even Dave Baldwin calls them atoms.
Yes.
The ions are atoms with missing electrons. Right?
Yeah, or
at least one or more.
Yes. Then there are photonic systems. There are companies like Xanadu, PsiQuantum, Quandela. Basically, the core principle here is to use light or photons to be more precise. And eventually, there are a few quantum companies developing platforms that are based on what we call neutral atoms. The companies that they work for is Quera Computing, but there are other companies such as Pascal, Atom Computing, Inflection, and Planck QC. And the basic idea here of using neutral atom, or actually the promise, is that they're relatively easy to scale in terms of number of qubits. They are good to program, and they display also relatively long coherence times. I just wanted to give you a snapshot of our company. So actually here is myself, this is my daughter, and we have a number of colleagues here during one of our Quera's parties. And Quera was born back in 2019 as a spin-off of Harvard and MIT, so it's really a local company. It's very much integrated within the Boston academic and innovation ecosystem. We moved to our current building in 2020, really at the beginning of the pandemic. And in November 2022, we actually connected our first quantum computer to a public cloud, which is the cloud service provided by AWS. The service is called AWS Bracket. That is a service that provides access to different platforms of quantum computing, not only to neutral atoms, but also ion traps and superconducting qubits. And today, up to now that we are speaking, our quantum computer has 256 qubits, and it is still the largest available on a public cloud. So if you happen to visit us at Quera, you will see that basically you will see it's still the largest quantum computer available to essentially anyone in the world. Over the past 3 years, we made a lot of interesting, we hit a number of interesting milestones in terms of really commercializing or making these systems available to a number of different organizations, not only academics, but also to the industry and governments. And we started working to the next generation of quantum computers that are based on a slightly different paradigm from the first one that we basically completed in November 2022. And I wanted to give you essentially a sense of how these two paradigms actually work. So let me kind of summarize the main features of neutral atom quantum computers. The dots that you see here in a pictorial way are basically atoms that are trapped by very tightly focused laser fields that are called optical tweezers. These systems can be relatively densely packed. The average distance is just a few micrometers. We can control the state of the qubit relatively in an efficient way. We can encode problems, and I will show you examples of this in a very flexible way. And by employing a slightly different technique, which is called digital or gate-based quantum computing, we can also design a sort of reliable path towards solving one of the major problems of quantum computing today, which is the presence of noise that induces error in the computation. So, what are these two different ways of computing? Also in classical computing, if we go back perhaps 80 years, or 80 or 90 years, the initial way of programming computers was based on analog operations, which are basically based on the principle that you have pulses, to control the state, the internal state of your computing device. In the case of neutral atoms, or in the case of quantum computing, the principle is essentially the same. What is actually changing from classical to quantum is the nature of the information. In the classical computing systems, the information is encoded in bits. In quantum computers, it is encoded in qubits. The second paradigm is called the digital or gate-based, where we now have essentially an algorithm that we break down in different pieces, and each one of these pieces is encoded or basically represents a number of discrete operations on top of a number of different qubits, either at the single qubit level, like this operation that basically acts on top of this qubit here that is in a state 0, or this operation that actually has or acts on two different qubits simultaneously. And there are a number of interesting features that I don't want to, to discuss too much in detail, but if you're interested, we can go a little bit more into that. So what are the atoms? What is the main basic architecture that we can work with our quantum computers? Well, at Quera, we decided to work with a specific atomic species, which is called rubidium. As you can see, rubidium sits in the first column of the periodic table, and one of the properties of rubidium is its relative simplicity in terms of electronic structure. In particular, it is an alkaline atom, meaning that there is only one electron in the external shell. The other important feature of rubidium is that you can control the states of this electron, this external electron, in terms of optical lasers, so lasers that work in the optical regime. So, as you can see, the way in which we encode information, or the way in which we encode the basis states of the qubit in a rubidium atom, is just by focusing on the electron that populates the external shell, and then with the laser we can induce transitions between one of the ground state, or one of the states in the ground state of the manifold of rubidium, and one highly excited electronic state that, technically speaking, is called a Rydberg atom. I don't remember if we heard the word Rydberg in the presentations before, but actually Rydberg was one of the first researchers that identified the features associated to Rydberg, what are called nowadays Rydberg transitions. So in particular, there are some properties of atoms from the quantum mechanical standpoint that are called principal quantum numbers. So in general, you can associate many different quantum numbers. But in the case of Rydberg atoms, the idea is that we can excite this electron from the ground state, let's say n equal 5, if I'm not wrong in the case of rubidium, to a principal quantum number that can be as far as 70, 100, or even in certain experiments it can reach very large quantum numbers like even 200. And of course, if you pump too much energy into this electron, what happens is that you ionize the atom. So you basically go from a neutral system into an ion, essentially. And we don't want to do that in order to make our computation actually effective. I just wanted to mention, just for completeness, that of course our choice is not unique. There are other teams, both academic as well as in the industry, that are using different type of atoms. And the reason is that there are certain types of properties of those atomic species, like ytterbium or strontium, which are two alkaline earth atoms, that basically make computation potentially more reliable in certain types of regimes. And now I just wanted to jump from basically the platform to show you how these computers are actually made of. And here we have some 3 colleagues of mine that were actually building this device some time ago. And the final result is given by these nice, these racks that are the same racks that you could find also in a classical supercomputing system. But the real cool stuff, actually the quantum level, takes place within these big black boxes. You can see some optical tables where we store both lasers as well as the vacuum chamber where atoms and the computation actually takes place. And I also have a video. I don't know if I have time to show you, to show it in full, which you can. I will also have the QR code of this video in the next slide. So if you're interested, you can then just scan it and watch it at home. I want to see if I have.
Quantum computer, a breakthrough in quantum technology.
This is more
Our
kind of
system harnesses
a
the
marketing type of video. So listen it with a grain of salt.
and scalability.
But the cool stuff is that there are some cool images of how our quantum
Unlike
computers are
classical
actually
computers, they
built.
use bits which can be 0 or 1. Quantum computers use quantum bits, or qubits. Qubits can be in a state called superposition, meaning they exist as a mix of 0 and 1 instead of just one or the other. Along with entanglement and quantum interference, this allows quantum computers to explore many possible solutions at once, potentially solving problems beyond the reach of classical computers. In our system, qubits are individual neutral atoms, and their zeros and ones are encoded as different energy levels of the atom. This is a neutral atom quantum computer. Let's look at the key technologies that make it work. Step 1. Trapping individual atoms. We start by creating a cloud of ultra-cold atoms inside a vacuum chamber, isolating them from disturbances to preserve their quantum states. We then trap the atoms using lasers in a magneto-optical trap, MOT, cooling them to microkelvin temperatures to prepare them for quantum computation. Step 2. Arranging the qubits with optical tweezers. Next, a spatial light modulator, SLM, creates optical tweezers, precisely positioning atoms into a structured qubit array. An acousto-optic deflector, AOD, dynamically adjusts these tweezers, enabling individual qubit repositioning for advanced quantum algorithms. Step 3. Performing quantum computations. Once the atoms are in place, laser pulses manipulate their energy states and generate interactions between them. This process creates entanglement, a fundamental quantum property that allows qubits to process or store information in ways classical bits cannot. Quantum gates, which are the building blocks of quantum algorithms, are applied using precisely controlled laser pulses. These gates enable the computer to perform complex calculations, similar to how logic gates work in classical computers. Finally, a highly sensitive camera detects the fluorescence emitted by the atoms to reveal the qubit's quantum states to extract computational results. Neutral atom quantum computers have several key advantages over other quantum platforms. Scalability. Optical tweezers allow precise positioning and control of atoms, enabling large-scale qubit arrays. Connectivity. Any neutral atom qubit can be moved to interact with any other qubit, enabling efficient algorithms and innovative quantum error correction strategies. Room temperature operation. Unlike many other quantum approaches, neutral atom computers operate at room temperature, reducing complexity and energy consumption. While still in development, neutral atom quantum computers hold immense promise. By combining the power of nature's qubits with cutting-edge engineering, we're paving the way for a new era of quantum computation, one with unprecedented scalability, accuracy, and real-world applications.
So I hope you enjoyed it, but can we go to
Whereas neutral...
that's too much. But I wanted to show you in practice. So this is the QR code if you're interested.
One point about this room temperature, perhaps, is, of course, the atoms have to be prepared in a magneto-optical trap, so they're also cold. But I think the point here is that with a Google or IBM superconducting qubit, which always have to be refrigerated at
millicavity.
I think helium temperatures at all times, I think this is the advantage.
Yeah, the good point that you're making or saying is that the atoms per se are relatively at very low temperatures because there are laser trapping techniques that allows you to basically cool them down. But then they are almost in vacuum, and you can isolate them from the external environment. So even if the environment is at 300 Kelvin, basically the atoms don't feel the external temperature. This is very different from a chip that you need to cool down, and that's why you need all those cryostats and those chandeliers to basically cool them down and control them to very low temperature. So even though this is really purely a classical control of quantum computers, the effect is actually very different because cooling systems down, needing those fridges or cryostats is also relatively expensive. And neutral atoms, not only in terms of academic application, but also really at commercial level, they are much cheaper to build and to maintain compared to, and to operate compared to other types of technologies. So thank you, Sam, for that. That's really interesting.
I would also think that it
Yes.
has a much less of environmental impact.
Yes.
So what other environmental impact does, no, I'm curious,
I
right?
can-
Like
I can give you
sourcing
some numbers.
materials and
Yeah.
stuff, like,
Yeah,
right, everything has some sort of impact, so,
sure.
right?
I
That's
think-
something we talk about with the kids with AI. AI is great,
That's good.
but like there is a valid environmental impact every time you go onto ChatGPT and have it write a paper for you.
I
Right,
can
so
give you
like-
numbers. I can give you numbers. That's a great point. So, for example, these computers that we build have a power consumption of the order of 10 to 20 kilowatts. For you to have an idea, these are just 2 or 3 hair dryers that you switch on simultaneously. If you look at AI applications in really the biggest supercomputing centers, there are many here in the US, not only from big companies like Amazon or Google, Microsoft, but even in national labs. The power consumption is of the order of 10 to 40 megawatts. So these are really more than 3 orders of magnitude, typically larger than what a current quantum computer can actually consume, is actually consuming. So this is one of the reasons why some companies, and you probably heard it on the news, are looking for nuclear power to start to basically run these classical big high-performance computing centers. So we're really talking about 2 very different technologies here in terms of environmental footprint.
And what about, what did you say, rubidium, is that what
Yeah, rubidium.
you're?
Yeah.
How, like, sourcing that, is that an element that is robust and, readily available on the Earth? Is it rare? Is it,
That's a good point. So first of all, we need very, very little amount of rubidium, very small amount. And in terms of waste, maybe, Hossein, do you want to comment on that? I don't think it's really
No, I
an
think
issue here, right?
it's essentially a basic metal, it's an alkali metal, but the amounts that they use for these, for instance, in one of these 256 qubit, I don't think it's even a milligram or maybe.
Yeah,
So
it's really, yeah.
it's a- So, each of those things is an atom.
It's
So
a
if
single
you
atom.
have 256 is 16 by 16, so
Yep.
256 times.
No, if you take a more, you have to compare these numbers, this number here, these dots, which are single atoms, to the Avogadro number, which is 10 to the 23, So before getting to 10 to the 23,
Yeah.
we can run it, actually we can run it for years before actually we need to replace the rubidium inside of any of the machines. So that's the,
Thank you.
then the big point, so just to make things, I wanted to compare the level of energy consumption. But the real comparison we need to make is the level of utility of these 2 different technologies, so AI and quantum. And at the moment, we are not yet, at the point where we can have processors that can, have a real impact for useful or real life applications. The impact that we can have, just to complete my comment, is related to essentially scientific applications. So the whole idea of quantum simulation that I was mentioning before already allows you to get results that would be, even hardly imaginable in the case of really classically computing the behavior of certain types of quantum systems. So you can, in principle, use these devices purely for scientific discoveries. And this is what we really enjoy, and I think this is one of the reasons why we have so many scientists, in particular physicists, working on applications of quantum computers for pure scientific discovery. And here I wanted to show you essentially how these quantum computers actually work. So QPU stands for quantum processing units, and is essentially generalized, if you like, the concept of CPU and the GPU. And each one of these dots that you see that are filled by a circle are actually atoms. And we start with a configuration where basically all these arrays are unsorted. So we start essentially with random placement of atoms. And then we have algorithms that move these dots to the center, which is actually the computational area, the computational region. And then once we sort it, we get here. So this is essentially the second step. And you see that this array is almost fully filled. There are some empty spaces. And then once we get here, we start programming the quantum computer. So we run a certain algorithm. And after the algorithm, we need to take measurements. And the measurements, as Christian was explaining, are probabilistic in nature. They are not deterministic in most of the cases. And what you see here is that after we perform the measurement, we can basically detect the position of the atoms. And when when we see an atom, we basically say that we record 1. When we don't see an atom, you see these two empty dots here, you record 0. So essentially, after the computation, we take a snapshot of the state of the atom, okay, which we translate eventually into a sequence or an array of zeros and ones. And once we get these zeros and ones, if we are, for example, encoding a certain message into our computation, like in the example that we heard in the previous presentation, we are able to extract some information that we can eventually read out, by reading it or by visualizing into a plot or something else. Okay? So let me show you in practice how this works in real time. So you see that, I think this is actually in real time, so you see the atoms here that are stochastically trapped by the optical tweezers. Then we arrange them into this configuration, which is a square lattice. And eventually, in step number 3, we take pictures, and you see that from snapshot to snapshot, the state of the system actually varies. So you almost never see for a system of, this is 6 by 6, so 36 Newton atoms, you almost never see the same state. And things become even a little bit more dramatic when you change kind of dynamical protocol. So you want to create really a kind of random state or random superposition that Christian was explaining before. And you see here that for this picture here, we would expect really 50% of atoms in the 0 state and 50% in the 1 state. And you see that this actually gives rise to very different types of patterns each time that we take a different snapshot. So how do we actually program them in practice? So let's imagine that we have a tower, we have a quantum computer at QERA. You are sitting at home. You can actually look at some more details about how to program these quantum computers here in our public GitHub repo. So it's basically a website where we explain how to effectively program these quantum computers, and we show their capabilities. What we see here is an array of 9 atoms. So we label them from 1 to 9. We can arrange them in parallel rows. And the minimum distance between the atoms is of the order of 4 micrometers. So 4 times 10 to minus 6 meters. And we have a computational region that nowadays we increase it a little bit, but it's of the order of a few tens of micrometers. Okay? Now there is another interesting, purely kind of quantum phenomenon associated to these atoms, that is their intrinsic uncertainty, delta R. Delta R is the average uncertainty on the distance between the atoms. That is related to the fact that we have atoms that are trapped within the optical tweezers, but atoms, as we heard in the first and second presentation, are waves. So at each time we measure them, actually the position changes slightly, from snapshot to snapshot. So there is some uncertainty in the location of these atoms. Then there are some other constraints that come from the optical, the optical implementation of the way in which we control neutral atoms. The average distance, the minimum distance between the rows is always at least 4 micrometers, and so on. So once we create this array, what do we do? Well, we need to we need to operate the quantum computer by flashing some laser light into these qubits. And the laser light essentially translates into what we call pulses, okay? And the pulses control certain dynamical properties of the multi-qubit system that we create. These pulses control parameters that we call omega, and technically it's called the Rabi frequency, delta, which is called the detuning, or the phase associated to the laser field. And you can see that really, you can program, you can design different types of pulses. So a pulse which has the shape as a function of time. You see that the typical, or actually the maximum amount of time that we allow for the computation to take place is of the order of 4 microseconds. So you can design this pulse here. You can design a slightly different pulse for the case of the second parameter, and then you can even create a kind of step function for the third parameter, which is our phase. The question is, why don't we allow for much longer computation? Right? Does any one of you have any idea why we don't allow for the computation to take place for a millisecond or a second, for example? You're not allowed. Well, there are many reasons, but there is one relatively simple to explain, which is associated to the fact that, and I think I heard this motivation in the first presentation, when Francisco actually was showing the function of lasers, I think, and which is related to the nature of these electronic excitations, which are called the Rydberg states. And these Rydberg states can spontaneously decay, or these Rydberg electrons can spontaneously decay after some time into the ground state. So this is actually a source of noise which translates into a source of error into our computation. Why is it that? Well, because if we wait too long, instead of detecting a 1, if the electron spontaneously decays, we will detect 0. And this is kind of unwanted, otherwise we will get a purely classical result. Okay? So we have to constrain the duration of the algorithm to a well-defined amount of time in order to not to avoid the presence of decoherence, noise, or other types of effects. Good. I think I have 2 minutes.
No, there's time, but I think this point, which I think Tommaso just raised, is actually almost like capsulizing what you sort of learned. This is spontaneous emission. Okay? Is this light that we also see is the so-called spontaneous emission is a completely quantum mechanical process. Okay? It happens in classical light, but its origin is completely classical. Quantum. In a classical feature, okay, the moon doesn't just radiate and collapses onto the Earth, right? It doesn't. But electron does in the atom. Without anything, it's a completely so-called vacuum fluctuation, which allows it to decay. So no atom can always remain in a Rydberg state. It will have to, after some time, decay. And this is purely quantum mechanical. There's no classical equivalent.
How much time do we have? We have because they have to go back to.
Well, they need to leave, but maybe another few minutes. Is that okay?
Yeah. If we could be done in the next 5 or 10 minutes.
Yes, I think 5 minutes should be fine. So I will not go through all of my slides, but let me just show you perhaps an example of how we go from here, which is really the low-level programming of a quantum computer, into the design essentially of an application and how we can extract real results out of this. So there are other ingredients, so perhaps this is actually better to skip it. An important mechanism behind this technology is called a blockade, which has to do with the very strong interactions between atoms that populate these highly excited Rydberg states. That basically gives to this doubly excited state so much energy that you will not be able to populate the system of 2 Rydberg atoms simultaneously. And how does this translate? Well, it translates at a practical level, so if you want in the terms of usefulness of this computation, into a constraint that can be encoded into our quantum mechanical system. For example, the fact that we cannot accept the simultaneous, so if you imagine to be able to create this array, and we'll show a realistic representation in a minute, then these two close-by atoms or close-by dots cannot be colored with the same color simultaneously. So for example, you cannot have a Rydberg excitation here, a red dot, and another one here. Okay, this is due to the very strong interaction between these two different atoms. The applications of this are several. And there's the mechanism, or actually the kind of configuration that you would like to create out of these arrays are called the maximum independent sets, which are a specific type of combinatorial optimization that you could study, for example, in mathematics, for those of you that are more interested into this type of mathematical problems. But actually there are many real-life applications. If you are interested, there is this very kind of high-level paper that we published three years ago on how quantum computers can actually solve this problem of independent set or maximum independent sets. And you see that one of them is the so-called antenna placement. There is a store location. I will show you an example in a little bit. And this is actually another kind of telecommunication problem. But let me show you an example in practice, and then I'll probably stop here after that. So let's say that we have this map of our favorite city, Boston, and we identify, we are the owners, let's say that we are the owners of Dunkin' Donuts, okay? And we want to create a potential or many new locations for our stores. Now we identify, we go around the city, and we decide that there are many empty shops that we can in principle, open new stores of Dunkin' Donuts. So they all belong to us, okay? We are the owners, we are extremely wealthy. But then there is a problem. There is a problem. What is the problem? The practical problem. Let's say that I decide to open a Dunkin' Donuts or a store here. What happens is that, okay, I open it there, but I don't actually want another store, another Dunkin' Donuts, to be very close to the first one, because otherwise they would start competing for the same customers. Okay, if they are too close, let's say they are half a mile close to each other, and a customer would be kind of confused, and I will just dilute my resources by opening two stores instead of one. So actually what I want to do is, I want to solve a combinatorial optimization problem that essentially maximizes basically the possibility of opening as many stores as possible, but with the constraint that I don't want two stores to be too close to each other. Otherwise, I will just wasting my resources. So at the end of the day, this boils down to solving what is called the maximum, or finding one of the maximum independent sets of this network. Here, the network of possible locations of my stores. So the question is, okay, why are you, Tommaso, telling me this? How do I solve it in practice? And why do I need a quantum computer? How can I solve it with a quantum computer? Well, one way is to first reproduce with our technology. So we take our quantum computer, we take our atoms, we create the same grid. Okay, you see that the topology of this array is essentially the same as the one that you see here. Of course, distances are scaled down by several orders of magnitude, because here we're talking about probably miles distances between different dots. Here we're talking about micrometers. And now what do? I basically get back to the concepts that I showed in the previous slides. I will design the pulses, okay, to excite some of these atoms in a particular fashion. Okay, the design has to be optimal in the sense that I really want to find some useful result. And then what I need to do is I take a measurement. I take that camera that you've seen in the video, I take a measurement, and I basically identify the potential. Basically, what I do, I take, I again translate these locations into zeros and ones, and then what I do is I basically get back to my map, okay, and the ones that are basically not where you don't see the atom are my optimal store locations. So you see that in this configuration here, unless I made some mistakes, or actually the computer has made some mistakes, which is also possible, because the measure is actually probabilistic. What I observe is that none of the shots or the locations are actually near to each other. So through this basically paradigm of analog quantum computing, I was able to solve actually a problem that is potentially practical of practical utility. Yes, you have a question?
Yeah, so if you, like, in figuring out stuff like this, are you able to take into account other factors? Like, for example, if you actually are Dunkin' Donuts and want to figure out optimal locations, are you able to take in other factors, like, I don't know, like population density in different places to figure out where to put locations that might be closer together but higher population than other places?
That's a great question. So that could potentially be done by for example, deforming the original network into a kind of an artificial network that could take into account these additional factors.
So it's possible to do with.
In principle, you could do that, or you can design what we call a quantum machine learning algorithm. So you start from there, okay? You start from this network again. And then at the level of what we call post-processing, so when we get the measurements, you can down-select all those positions that takes into account additional constraint that you want to treat just purely on a classical level.
Cool.
So that's an excellent question. Very, very good question. Yes. Okay, so I think that I could transition to a kind of different topic to make it even more exciting, but for because of time constraints that we cannot unfortunately avoid, I prefer to stop here. And of course, feel free to reach out to me. I think that I also have my email at the end, or not. Or if not, you will find some information on either on our YouTube page or on LinkedIn, or just ask me and I will give you my email address.
Do you by chance have a business card?
I forgot my business card. Actually, there is, I think, my colleague.
I have Yelisa's.
You have Yelisa's. You can reach out to Yelisa or to me. Yeah, it's the same.
Okay.
Before, in the morning, there was a colleague of mine, Yelisa, that actually organizing many outreach activities related to Coera. So really at the level that is probably not so much detailed as the things that I was telling you about today, but still in a probably much more engaging fashion. So thank you so much for your attention.